Good morning. We're going to finish out this alcohols, the alkyl halides. There's only one problem left on there. We'll finish that out. And then we're going to start a section on organometallics. And we'll keep pushing with that until we finish it. All right. All right. 16 logged in. Wow, that's it. We'll wait a couple of minutes and then we'll start. I'm gonna go ahead and so the handout, I forgot to put that in the announcement, so I'm gonna go ahead and upload that here in the chat, so you'll have a chance to grab it. Because I forgot to tell you which one to get. I sent the announcements out yesterday. One second. All right. So the handout that you'll need for this section, I just uploaded. So you can just download it, grab it, and annotate it, print it, whatever you want to do with it. But that's the handout that we're gonna be completing through this section. So let me go ahead and share my screen. All right, so I think we left, the last question was here, and the one above it, you have to do on your own, but I just wanted to run through this real quick. So it's asking you about the product of the reaction that's shown. And it's actually, let me just show you what the product is. So this is the product. The expected product is this. But it's not observed. Right? So the question actually gives you a hint as to what happened. All right, and if you know for this particular reaction, you know the mechanism. If it's a secondary alcohol and you're treating it with HCl, what's the main intermediate that you're going to get from that? Using that set of conditions. Right, this is one of your intermediates. But what happens to this intermediate? Anybody?
Does it become like a living group and
Yeah, hydronium is a leaving group and is going to leave and create a carbocation intermediate, right? Right here. Sorry about that. Right, and now you can see here, now you have a secondary carbocation. Right, and so the secondary carbocation, I'm going to show you what happens, and then you can tell me what happened. All right, so that's what that becomes. Let me do this. All right, so if you look at that other cation that I have shown on the right, what changed?
The CH3 came in to the bottom.
Yeah, so what do you call that? What do you call that when you move a bond or an atom and a pair of electrons from within a molecule? What kind of reaction is that? Anybody remember that from part one?
Is that a rearrangement?
It's a rearrangement, right? So in this case, the type of rearrangement that happens is called a methyl shift. Right, so I'm actually taking this entire sigma bond and I'm shifting it to here, right? So that methyl group is going to move over. And now you have a tertiary carbocation, which is more stable. Right, so now you've generated a more stable carbocation. Most of the times when you have rearrangements of cations like that, the purpose is for stability. Right, you go from a less stable carbocation to a more stable carbocation. Right, and this is why you get this product, because that's what chlorine, sorry about that, that's what chlorine is going to attack, that rearranged cation. So now this is going to come, better not do that. Right now, this is going to come and attack here. Right here, boom, just like that, and that's going to give me my product. And the arrow pointed to the wrong one, sorry. Let me, I got a better way to do that. I'll move this other stuff. Let's move that over. All right. So, hold up. So this is my final product, right, from that reaction because of the rearrangement of the secondary cation to a tertiary. All right, so are there any questions about that?
The mechanism it was a rearrangement mechanism?
Yes.
Okay, just checking.
Yeah, so the mechanism that we went through is the same that we discussed when we used HX, but when it got to the carbocation actually did a rearrangement to give you a more stable carbocation, right, through a methyl shift. All right, so let's switch gears, and we're going to begin discussing organometallics. So what's the date? The 3rd. Right? All right, so I put the handout. If you don't have it, I put it in the chat. Let me upload it again, just in case. All right, so the handout from today is already uploaded. So we're going to talk about today organometallics, right? And the terminology is exactly what you would expect. You have an organic part, which is the carbon containing part of an organometallic, and then you have a metallic part, which means that carbon is bound to a metal, right? So an organometallic, if you watch the video, you got the definition of it. It is a species that has a carbon metal covalent bond. All right, so got a covalent bond between the carbon and the metal. It's polarized towards carbon. All right, so the carbon is partially negative. And the metal is partially positive. So the dipole is going towards carbon, and it is a type of carbon nucleophile. Right, so carbon is nucleophilic. And there are different types of organometallics. Most of the time when you make them, it's always synthesized them. They're synthesized at low temperatures, and they're also synthesized in aprotic solvents because they can, if they are nucleophilic, then they can also be basic. And so if you put a proton source around it, then it's just going to quench the organometallic. Right. All aprotic means is that the solvent doesn't have any protons. It's non-acidic, right? So water, alcohols, acetic acid, things like that, you wouldn't want that around your organometallic. And the reason, again, carbon is nucleophilic. So if I have a carbon metal bond and I add in H plus, right? I'm going to end up protonating that carbon. And let me do this. Cut down confusion. Right. So you need to do this in aprotic solvent so that your organometallic species doesn't get protonated and quenched, right? Then it's no good. You can't use it for anything. All right. So these carbon, metal, covalent bond, organometallics, we're only going to discuss 3 types, and then we're going to talk about how to make each type and what they're used for, right? So we're going to talk about Grignards, where the carbon metal bond is between carbon and magnesium. And then we're going to talk about really 2 types, because one type is a precursor for the other. So we'll talk about Gilman reagents, where your carbon metal bond is between carbon and copper, right? So for the Gilman, copper is your metal. For the Grignard, magnesium is your metal, but they all react in a similar fashion. All right, so and we're going to talk about how to use them. And one of the main uses for these is what we call coupling reactions. So coupling reactions where you form carbon-carbon bonds. And this is a really powerful class of reactions, and you'll be hard pressed to find any synthesis of any natural product or any compound that doesn't make use of at least one step where you have some type of organometallic coupling. Maybe it's not a Grignard or a Gilman, but there are also like catalytic methods to make carbon-carbon bonds. So you'll be hard pressed to find any organic synthesis of any type of natural product or any type of large molecule or macromolecule where you don't have like at least one of these reactions used, or one of these types of reactions, right? So let me give you a brief introduction to that, and then we're gonna go back and talk about how to make each one of these organometallics, right? So for the coupling reaction, if I take and this is also under the umbrella of the application of alkyl halides, right? Because we've been talking about how to make alkyl halides. And so now we're going to talk about one of the uses of alkyl halides. So if I take let's just say a simple Grignard like this, right? So this is my organometallic, and I reacted with an alkyl halide, right? What this type of reaction does, it's a coupling reaction. I'm going to end up putting carbon pieces together.
Bless you.
To make go ahead.
My bad, I'm good.
All right. All right, so the coupling part is when I make a new carbon-carbon sigma bond, right? So without going through into too much depth with this, because we're going to study it at length shortly. The final product from this is a new bond between those two carbons. Right, and then a side product of magnesium diiodide, right? So I have a kind of a simple method for thinking about this, and it's to take the carbon. We're going to talk more about this later. Carbon metal, which is your organometallic, plus your alkyl halide. And when you react them together, you get a new bond between C and R, and then M and X. All right, so let's talk first about the Grignard and how to make it. And I have there's a page in the handout that discusses it, how it works. It shows the Grignard happening as a radical process, but it's not a radical chain reaction, right? So it doesn't go through the initiation, propagation, and termination steps like a allylic bromination would or radical substitution would. It doesn't work like that. So you have your, right here, your magnesium, right? And magnesium has 2 electrons. So it donates an electron towards an alkyl halide, right? And I'm gonna show you this with a real example, but it donates an electron to facilitate the cleavage of the carbon halogen bond. And then you end up with a radical here, and then a magnesium with 1 electron. So those two couple together in the second step. You can see that right here, right? And then you end up with your Grignard. Right, so let me show you that on just a regular example. So in order to make a Grignard, right, you need an alkyl halide. Right, so I'm going to just start out with this. You need magnesium metal, and you're going to do this at low temperature, so minus 78 degrees Celsius, and then you do it in an aprotic solvent again, ether, right? Again, you don't want any protons around your organometallic, because it's just going to do proton transfer and quench, and it's not going to be useful. All right. So from this, I'm going to get a magnesium, and then the iodine is here. All right. And again, the way this works, magnesium has a pair of electrons. Zoom in on that. Now, iodine, you know, is a halogen, so it has 3 lone pairs. So it's going to donate 1 electron here and help facilitate this bond cleavage. All right, so now you have a radical here plus I minus plus magnesium with 1 electron and a plus charge, right? Because it gave 1 electron away. So now when magnesium and carbon see each other. Let me move this around because I want to make this as painless as possible. I'm not sure how painless organic is though. Right? You want to do this, couple them together, and then you end up with that carbon magnesium sigma bond like so. This is still positive, and then the iodine is coming here and hanging out to make a salt with magnesium. All right, so that's how your granules are synthesized. Now imagine, again, if you were to just add H plus, or have some type of, if you did this in a solvent, like acetic acid or water or ethanol or something like that, right? All that would do is give you this, right? You don't want that. That's bad, right? So you want to do this in an aprotic solvent so you can have that granular and use it to do other types of reactions, like your coupling reaction that I just showed you up top. We're going to do a bunch of those though, so don't panic. All right. Any questions about the granular synthesis? So it's radical. The mechanism is radical, but it's not a chain reaction. All right, so again, one of the applications of alkyl halides is to make organometallics. Like that's one of the major applications. So first we studied how to make alkyl halides, and now we're looking at how to apply them. And one way to apply them is to use them to make organometallic reagents, right? All right, so this is granules, and then let's talk about the other organometallic that we're gonna study, which is the Gilman reagent. So I'm just gonna add a new page for that. All right, so the Gilman, again, it's a copper organometallic, but you start with an organolithium. Now you're going to start with an organolithium compound. Organo meaning carbon, and then lithium for lithium metal. So the way you make the organolithium is very simple. It's just like making a granular. You start with 2 equivalents or 2 moles of lithium. And then you react that with some alcohol. Let's stick with the same alkyl halide. All right, so you react that with this alkyl halide. Similar mechanism also, but lithium has only 1 electron. And so that's why you need 2 equivalents of lithium, because one of those electrons is going to be donated to facilitate the Ci bond cleavage, and then the other one will be donated to make the lithium carbon bond. All right. So what you're left with is this. Sorry. See, that's your organolithium plus lithium iodide. All right, and if you want to see how that works, you have a lithium here with 1 electron that's going to donate and help to facilitate that bond cleavage. Hold up 1 second. Like so. All right, so you're going to end up with lithium iodide plus this radical. And then I'll react that with another lithium, the second lithium, which has 1 electron to give away, right? So that's where my lithium carbon bond is going to come from. So I'm going to put those two together, and then I'm going to give me this, right? Plus lithium iodide. All right. So with the organolithium in hand, now I can make my Gilman reagent. So to make that, we're going to add the organolithium to copper iodide. And again, I'm doing this at low temperature on purpose, because at low temperature, you can kind of slow the reaction down, make it more selective. And most of these reactions are exothermic, so they're very rapid. So if the lower the temperature is, the more you're able to control the rate of reaction. All right, so I want to take 2 of my organolithiums. That I made up top. Right, 2 of those plus copper iodide. When I react those 2 together, I'm going to get out my Gilman reagent. And again, I'm doing this at low temperature. So let's say minus 78 degrees Celsius. And then I'm doing it again in aprotic solvent like ether or THF or DMF or some other solvent like that. And I'm doing that on purpose because I do not want to quench my organometallic. All right, any questions? Right, I had a friend of mine, I tell this story every time I teach this section, but I had a friend of mine as a grad student who was making a Grignard for use in a larger synthesis. And he kept, every time he made the Grignard and went to take an NMR of it, or tried to take an aliquot out so he can get an NMR, he would notice that all he got was like an alkane. So what he found out was that his flask, because you have to do this thing with like a cold finger and slow addition and all this stuff. And what he found out was that his flask wasn't sealed up just around the neck. He didn't have enough joint grease on there. And the condensation from the ice bath, from the cold bath, was getting into the flask. So he ended up having to set the flask up, duct tape, or we use electrical tape, put electrical tape around all the joints so that no water could get in. And he finally got it on like the 5th try because he couldn't figure out why the Grignard kept quenching. But these reactions are very sensitive to the condition. So you always want to use an aprotic solvent. You want to keep it dry as possible and at low temperature, right? So here, when you make your Gilman reagent, you end up with copper, and you have 2 equivalents of your organolithium, right? And so both of those organo pieces, let me zoom in on that. This is a 3-carbon chain right here. Both of those are going to end up on copper in a covalent, with a covalent bond between copper and carbon. All right, so I got this carbon right here and this one right here that was bonded to lithium, and now it's bonded to copper. All right. And then copper actually is negative. So it has a pair of electrons, it's negative. And then the other lithium salt is out here. or the other lithium metal, right, is out here. So you have a ionic bond between copper and lithium and a covalent bond between copper and carbon. Right, so you can see right away that this is going to act as a nucleophile. And this is a great coupling reagent. The only drawback is that when you use it to couple with another alkyl halide or some other species, you only transfer one of your groups, right? So only one of these groups is going to get transferred. The other one is trash. So a lot of times you want to put on one group that you want to transfer, and the other group, you put something on that you don't care about, that you can throw away. Because once you do that one reaction and transfer one of those groups, the second group is not coming off. Like you can't go back and use copper again. So let me show you real quick what other types of species you can use to make granules and then cuprates, and then we're going to start looking at the reactions, right? So if I took an aromatic put it right here. So if I took a like iodobenzene aromatic and reacted that with magnesium metal, low temp, and in ether, right, I'm going to get out an aromatic granule. Right, so it works with that. It also, if I have a vinyl iodide, like a vinyl halide, and use that with magnesium right, I'll get out a vinyl green. And the reason I'm using like iodine is because that's the easiest, most facile reaction, right? You can use iodine, it can be bromine, or it can be chlorine, but iodine is the most facile out of all of them, because that's the longest, that bond is long and it's weak, and so it's easy to get that metal to insert in it. Right, by the same token, with your Gilman reagents, they don't always have to be alkyl. You can use other types of species, just like up top. Right, you can use an aromatic. If you have an aromatic organolithium, then you'll get out an aromatic cuprate. Same thing, if you have a vinyl lithium, you'll get out a vinyl cuprate. So it just depends on the scope of the reaction. Is pretty wide. You can use a lot of different types of substrates to make these, right? But again, the synthesis is not just random. You make these based on what you need, right? So if you want to do a reaction where you're coupling a vinyl group to some other alkyl halide or some other group, then that's the type of Gilman reagent you want to make. So everything is based on what you need, right? You synthesize what you need. So it's not just me throwing something in a reaction vessel and praying for, for the best. Synthesis is very strategic. So you always have your synthetic target in mind as you make your reagents that you need, or you know, sometimes you have to buy reagents and things like that. All right. Any questions about how to make Grignards, how to make cuprates, or the scope of the reaction, or anything? All right. And again, you always want to use low temperature and aprotic solvents. Aprotic means no H plus to give away. So you'll never do this in an alcohol. You'll never do it in an acidic solvent. You'll never do it in water, anything like that. All right. Any questions about anything we talked about so far? All right. Let's go to look at, we'll do a couple of examples, and then we'll stop and we'll pick up on Monday. So again, the overall theme is the synthesis and application of alkyl halides. One of the ways that we use alkyl halides is to make organometallics. And one of the things that we use organometallics for is to make new carbon-carbon single bonds. So let me put that in here. So we said this is the umbrella that we're studying under. All right, so we learn how to make alkyl halides. One of the applications is organometallic synthesis. And we use organometallics to make new carbon-carbon bonds. All right, and that's a huge goal in chemistry, in organic. Carbon-carbon bonds are not trivial, right? They're not easy to make. So if you have a method that allows you to make them and make them efficiently, that's a good thing. All right, so let's look at this first reaction, which is one of our coupling reactions. Right, and again, with the coupling reactions, we find CM and RX, where RX can be a alkyl halide. Sometimes the halogen can be replaced with a different leaving group, like a triflate or some other group like that, a tosylate or something like that. Well, I'll show you some examples of that because that's not here, but I'll add them in. So here, the strategy is simple. Find CM, find RX, and you want to put C and R together. All right, this is my goal. I want to make a bond. And you know, R is generic for for a carbon or a carbon containing group, right? So I want to find CM, I want to find RX, and I want to put C and R together. That's my goal. So over here, where M is the metal now, don't forget that. M is representative of the metal. So here, what type of organometallic is this? And where is the CM bond? Right, so I have magnesium as my metal, yes?
Yes.
So what category of organometallic is this? We only talked about two. It's either a Gilman or a Grignard. And a Gilman uses copper. So with magnesium, this is a Grignard reagent. right? So Cm in this case is what? The M is the metal, is that right?
Yes.
And then the carbon that's bonded to it
It's the C.
is the C. Good. So this carbon right here. All this other stuff, we're not worried about it, right? We're just worried about that carbon for now. So that's Cm. And then over here, X is normally representative of a halogen, or it can also represent my leaving group. So I'm looking for a halogen or some other leaving group in the place of X. So what is X over here on the right side? Iodide. Good. So this is X, and it's bonded to a carbon right here, right? So that's R. Are y'all following that? So what I'm trying to do, and we're not going to go through necessarily go through the mechanism of how this happens, because it's kind of, I don't want to say up in the air, but it's debated as to whether this is a polar mechanism or whether it's a radical mechanism. So we're not going to worry about the mechanism. We're going to focus more on the outcome. So what two carbons am I putting together in the product to make my new carbon-carbon bond? Right, all this stuff back here stays the same. The ring doesn't react at all, right? That's not a part of that's just a substituent on the carbon that I'm reacting. So that's that, and I'm gonna put that carbon back. This is a common mistake when we get to this section, is to fuse the two carbons together, but we're not gonna do that. All right. So that carbon is gonna be bonded. I'm gonna change the color so you can see the new bond. To this carbon right here. Can y'all see that? So that's what my product is going to look like. All right, fix that back. So this is my CR bond. And then over here, I have an iodine and then I have magnesium iodide. So I'm just gonna put those two together. All right, questions about that? And then of course, this is MX, right? So that's what I'm trying to couple together. CR, which is my main product. MX is going down the, well, not down the drain, but going into the waste. So we don't really care about that. All right, questions about that, about what just happened? All right. So we're gonna stop here. We'll pick this back up on Monday. If you need to rewatch the video, do so. If you need to look at the syllabus and read, well, not if, you need to look at the syllabus and look for this section on organometallics and read those sections in the text, as well as if you want to supplement that with something else, that's fine too. But we'll pick this back up on Monday if there are no questions. And then we're also going to expand this and talk about organometallics, not just doing coupling, but also being used to react with carbonyl. So that's the next step in this progression. So, but I'm not gonna send that video over the weekend. I'll send it next week. All right. Any questions? Other questions about anything?
I have a question.
Go ahead.
I submitted I think 2 assignments wrong, but it's only 1 attempt. Are you able to make it 2 attempts so I can fix it?
$10. Oh, I'm still recording. Sorry. Yeah, just shoot me an email. I'll go in and clear it out.
Okay, thank you.
No problem. And when you send the email, just make sure you put the exact assignment so I can just go find it and clear out that attempt.
Okay.
All right.